So friends, now we are into part B of probabilistic methods. Okay, and here we will be seeing error estimation in ML because it is used as a errors are used as a estimation criteria. Like I gave you in my last lecture, that 10 to the power minus 3 was a termination criteria. So this is one thing, and then likelihood estimation, it helps us to see the how far we are close to the real time data. Okay, normally for any data we call it is an estimate of that q head or q this thing bar is a indication of not the real value of the, like mean and q mean head. I'll come to that part, and then non-parametric methods. We have gone to the next this thing, Kolmogorov-Smirnov chi-square, and one more method we will be discussing. So let us start like this. Most popular approach for error estimation is root mean square method. It is nothing but you have all the x and y point. So here we have plotted on T this light this thing, and then E RMS error actually is nothing but y minus y cap y head, and then divided by n and whole up square and summation of all these I values, and like y cap is like a mean actually, you know. So that's how we estimate it. And this is a very important algorithm when we are training our neural network, and unless until the RMS error converges to the acceptable value, the training goes on. Okay. Yeah. So like RMS error, it starts converging to acceptable, almost like range from 0 to any positive value expressed in the unit of variables. Like RMS for a given population can range to 0 to 340. It is just a hypothetical figure that we have, but that becomes an acceptable value. According to RMS, the model is this, and then we have deep learning. As I mentioned, it is used as a termination criteria, or how the algorithm is getting each iteration will come to one reduction in RMS error, and finally the value actually. So this is basically for FT and all. I'll come later on. Probably here I'm trying to see the FT arriving to 1, with the time, and that is not a normal, but it is an equation of the line y is equal to ms plus c. This has a different context. I'll come to this later on. Okay, but one we saw RMS error, but this there is a standard normal error function, particularly in the context of normal distribution, where mu, that is standard normal, where mu is 0 and the sigma is equal to 1. Then it puts in the category of standard normal distribution, and it is expressed as 1 upon pi exponential minus t square dt. So this is called error function x. Okay, and the standard deviation for error function x is 1 upon root 2, 1 is equal to 1 upon root 2. Further assume that all the distance from error values will be close to the value. So here the way we have for standard normal distribution, sigma is equal to 1. For error function it will be standard deviation will be 1 is equal to 1 upon root 2. Okay, so this has to be remembered, and this is a t square we have plotted against t, and finally it stabilizes actually, like any CDF or something. So this is what error function, and it has got value ranging from minus 1 to plus 1. In between value is central value is 0. Okay, and then now you know that how accuracy is expressed. the accuracy is error free, or how we can have minimum error in our readings or in our estimation, and that is, so error is a measurement is specified in terms of accuracy. It is defined as the difference between the measured value and this thing. So measured value into the random, defined in terms of full scale of the reading. Absolute error, there are two types of error, absolute error and relative error. Absolute error is actual reading, measured value, and what is the true value, EA, it is called absolute error. And relative error function is called ratio of absolute value upon true value. Okay. So here it is a difference between measured value and this one, that is absolute value divided by xt. So this, for the sake of completeness, I am giving this absolute error and relative error, but generally we go for RMS error and other modes for our convergence criteria in machine learning. Now, if you remember, we have discussed maximum likelihood function. For the sake of continuity, I am providing here because under probabilistic method, and the maximum likelihood estimate comprises of if suppose we have a parameter theta, so len of theta and likelihood of theta parameter, okay, and if I take the gradient of the line del upon this, that is and so we should get 0 either at maximum or minimum. So here we are trying to have maximum value. So len theta should be likelihood function of theta should be approaching 0 when we have the gradient of the line, that is derivative of the parameter. Okay. So this is the above equation provide the value of maximum likelihood estimator. I think we have operated this particular function on our exponential distribution, and there in one of the previous class we have estimated the value of maximum likelihood estimator for exponential distribution, and that was lambda cap value. Okay, and inverse of that is mean time to failure that we have arrived. So that means apply this function and likelihood function definition on ft is equal to lambda into exponential minus lambda t dt, and then we had estimated this derivative, and we found out the maximum likelihood estimator for lambda, for exponential distribution. So that was the thing we had seen in that slide. Okay. So in that sense, we have done with maximum likelihood function. If you can relate to that old presentation, you will find there. So this part is over. Now next part in this one is interval estimation. Interval estimation or confidence interval estimation, whatever you call. Why it is necessary? Because this is one of the approach. Interval estimation is approach for characterizing uncertainty in probabilistic risk assessment. Because each data, traditionally we use point estimate, okay, but point estimate we know that intuitively they have uncertainty associated with that, and there we use log normal distribution to characterize the uncertainty. So that means if suppose component form the building block, that means they are at the root of any fault tree, then we provide the median value and then assuming that the component failure probability is having a log normal distribution, and that's why we have error factor. Error factor means the 90% confidence interval divided by the median value in log normal distribution. So that will give me error factor, and normally the practice is error factor of 3 or less is acceptable, but if error factor goes for human reliability and there are little rare events, if it goes to 5 and all, then 5 becomes the barrier. That means the reading is the value is not available at, if the for any data, if the uncertainty associated is very high, that means that data is not available, whether you apply Bayesian updating or any other method. So here it is, we are talking about the interval estimation. So suppose if the parameter is theta for the distribution, and we have a random variable x to xn, then the lower value will be theta L x1 x2 x3, and upper value will be theta u will be x1 x2. So here we'll find 90% confidence interval, here we'll find 5% to 10% confidence interval. We'll see in the future how we do. Then the interval estimation problem can be defined as that theta value lies between, here we can use the word lies between lower value, that is probability of lower value of random variable, and upper side that is 90%, so is equal to 1 minus alpha. Alpha is significance level. Okay. Slowly you will get, and if you multiply 100 by 1 minus 100, so you will get 5%, 95% confidence interval, like that. The speed of the term, the spread of the term is and then 100. It divides between lower and higher this thing. So interval estimation for normal distribution, we saw assuming random variable x1 to xn, and then on normal distribution it can be defined. Now we are talking about the normal distribution. Mu is the parameter of normal distribution, n sigma and standard deviation, they provide name of the normal distribution. Instead of calling normal distribution n mu sigma, we write. So we want to find mu and sigma assumed to be known. Okay. Consider a standard normal distribution, and then we have this z value, you are aware, x minus mu upon sigma. So now can we work on the lower limit and upper limit of this value that we have here. So we have x minus mu, these things are known. So we have that value, and how the lower value 1 minus alpha by 2, like in normal distribution on left side it will be minus z by alpha 2, and plus will be z 1 minus alpha by 2 is equal to 1 minus alpha. This is the standard expression of upper limit uncertainty associated with the normal distribution parameter. You can always say normal distribution, it is symmetric. So if you give one side, it will give. So normally the same figure should, but in practice we do not know exactly what is normal, exactly what is log normal. So you might see difference, but in principle speaking, we should not find these two values. So same value should be minus plus, but due to the specific variations and all that, because nobody will be ideal normal distribution, distribution will be standard or ideal normal distribution. So some variation can be there. Here 1 is alpha 2 x, this we know actually. The above equation can be written as follows for the x bar. X bar means sort of a, so we have x bar, that parameter, x, capital X indicates the random variable, its average value minus mu sigma into n, and again instead of z we have written these values, x minus alpha value and x plus this alpha value. So upper bound and lower bound for cap. So probability of this is equal to 1 minus alpha. Now let us rearrange the equation and all. This equation, and cutting the story short, we come to x minus t. Now we have suddenly brought this t distribution, when it depends on the sample size, when we can use t distribution. When the sample size is small, instead of normal we can translate it into t distribution also. T distribution is also called student's distribution, so you can refer that, but here the formulation is x bar minus 1 minus t alpha 2 sigma s. S is for population. So now we are talking in terms of t distribution, assuming t distribution to represent this, divided by, so mu now higher and upper limit 1 is alpha. Similarly for sigma square also we can see n minus 1. So what we are saying is, in short, we have got normal distribution, we have assumed to be z application, and now finally we are approximating it equal to t distribution and finding out the upper and lower bound of mu and sigma both. So this is about the normal distribution. And now confidence interval, let's say if we talk about the exponential distribution. Normal we have completed. Now lambda cap is equal to R, that is the number of failure divided by T, total accumulated time, that we all know that. Failure rate is nothing but failure divided by the accumulated time. So, chi-square applicability, there is a condition that 2R lambda divided by lambda cap is equal to nothing but 2 lambda t. 2 lambda t is a symbol term actually. So, this has been demonstrated, then it follows chi-square distribution. Why we are doing it? Because we are trying to estimate the upper bound and lower bound of chi-square distribution. Okay. With the 2R degree of freedom for the type 2 test. Please remember this very important term, type 1 test and type 2 test. Type 1 test is time terminated test and type 2 test is failure terminated test. Okay. So, for type 1, type 2, the degree of freedom, because finally you will go to the graph and try to plot exponential distribution plot, and you, so 2R degree of freedom, and here 2R plus 2 degree of freedom for time terminated test actually. And then confidence interval can be estimated for 1 minus alpha significance level with MLE maximum likelihood estimator of lambda. Why we are calling maximum likelihood estimator? You go back to the lecture where maximum likelihood estimator lambda was estimated for exponential distribution, and k is equal to R for type 1 test and k is equal to R plus 1 for type 2 test, and accordingly you know that this is a exponential distribution. Okay. So, this is, you know that even Poisson distribution you can approximate to the exponential distribution, and with that I think what we come here is integration, either you have discrete k to value varies to infinity and this model Poisson, and otherwise if you are continuous distribution then 0 to 2 lambda t f chi-square t, that approximation because we have got from here, it follows the chi-square distribution, and then 1 minus lambda. Okay. So, with this side now we get alpha by 2 value 1 minus alpha by 2, and for that we get, now what we have done, we have fallen back from exponential to chi-square distribution. Okay. The way we did from normal distribution to t distribution, and we have got this confidence limit here. That means 2R lambda by lambda, that quantity we were talking about is equal to chi-square degree of freedom. This R is called degree of freedom. Alpha by 2 is significance level. Okay, lower side and higher side is equal to 1 minus alpha range. Two-sided confidence interval we can write lambda. We can have lambda from here, reorganize the terms, and lambda has got a lower limit, upper limit divided by 2t. It is 2t, same as 2t here. Okay, is equal to 1 minus lambda. One side confidence limit 0 is equal to 1 minus, so it will be 1 minus alpha is coming 2R divided by 2t. That thing we have taken is equal to 1 minus alpha. So, for exponential distribution also we got the lower limit. Now, let us see how in this slide here this thing for lambda for exponential distribution we have estimated. So, it is for one sided, for two sided chi-square alpha by 2 2R divided by 2t 1 minus alpha chi-square 1 minus alpha to 2R plus 2d. So, that means if the now simple term degree of freedom is if number of failure is 4, so multiply by 2 plus 2, so 10. So, degree of freedom will be 10, and this will be give you the value, percentile value, that like suppose if it is a 90%, 95% confidence limit, so it will become 90%, 0.9 here. Okay. So, like that for upper limit 5%, 95%, so 90% confidence interval you will get. Okay. MTTF inverse of this will get MTTF. Okay, for one sided, and then lower limit, this will become a lower limit for this thing MTTF here, and this will be a higher limit, you know. So, and then finally if you want reliability bound also here, exponential reliability, it will be 1 on upper side, reliability 0 to this thing. So, we have exponential term, okay, and this is for lower limit, and the upper limit for reliability is 1 actually. Here we can keep estimating for the whole and draw the curve. Similarly, for two-sided also we have this curve. one time t is equal to 0. So it is time t0 means time whatever we choose at time reliability at time t is equal to 0, that we are telling. So at time t is equal to 0, the reliability will be this much upper bound and lower bound. Now this was basically for type 1 time terminated test. Now type 2 failure terminated test, same way the way we did for time terminated test, we can derive this equation, and they are here. There is an analogy or similarity between these two graph. Okay, so lower limit one-sided, two-sided, and here also mean time to failure will be lower limit. This will be infinity. Okay, and here we have lower limit and upper limit the way we had for this one, and finally reliability at this thing. So from chi-square distribution we can find out if we know the value of chi-square, nothing. If you know the degree of freedom, number of data points, and if you know significance level, you can estimate the reliability also. You can estimate mean time to failure also. You can estimate lambda also. Upper both the side limit and upper side limits actually. So the overview is like we had root mean square error, normal distribution function, error function we have estimated, and other error models just we hinted upon. That was done here, and then we have maximum likelihood estimator. You can complete it in the previous part and main part where lambda cap was estimated, and this part in the context of how probabilistic approaches are useful for confidence interval for reliability and all for machine learning actually. Confidence interval estimation, standard, normal, exponential, type 1 terminated, type 2 terminated test that we have completed. Okay, so yeah, so this way week 6/4 is complete. That is fourth lecture of 6th week is complete.